Hello, good morning and welcome to my course Basic Electronics Engineering. This course is generally made for BTech degree students of second year. Myself, Gopal Chakraborty, Assistant Professor, Greater Kolkata College of Engineering and Management, Baraipur, a college under JIS Group Educational Initiatives. Students, you can personally meet me at college premises, ground floor, physics lab, or you can also send me a mail regarding your doubt and query to my given mail address, that is godphysics6@gmail.com or gopal.chakraborty_gkcem@jisgroup.org. I have a YouTube channel. The link is given here. You can follow my YouTube page, as I have already uploaded lots of video as per your markout syllabus, and if you feel any doubt, any query, feel free to contact me. Now, the corresponding course pages are www.markoutexam.net, www.markoutwb.ac.in. The syllabus corresponding to this subject is already uploaded in the Markout website. You can find the syllabus through the given link. The title of the course is Basic Electronics Engineering, and the subject code is ESECE 301. It is under the category of Engineering Science course. It has a credit 3 lecture per week. This course is generally made for BTech degree students of second year, third semester. So, apart from all other departments, only the student of mechanical engineering department have to study this subject as a part of their curriculum of second year, third semester. So, for this subject, I am your subject teacher. Now, today the topic that I will going to discuss is basics of OPAMP based logarithmic amplifier and anti-logarithmic amplifier, and also the OPAMP based half wave rectifier and full wave rectifier. These topics are under module 2, that is operational amplifier and its applications. Prerequisite for this topic is elementary idea of semiconductor physics, and corresponding course objectives is to provide an overview of basics of OPAMP based logarithmic amplifier and anti-logarithmic amplifier. Also the OPAMP based half wave rectifier and full wave rectifier. So after completion of this topic, student will able to understand the principle of OPAMP based logarithmic amplifier and anti-logarithmic amplifier. Also they will able to understand the OPAMP based half wave rectifier and full wave rectifier circuit and its operations. So these are actually considered to be a possible course outcome for this topic. Now, before going to start with today's topic, I would like to remind you that I have already uploaded 4 to 5 videos. So students, you just go through that last 3 to 4 video class lessons as to know and understand the OPAMP as a logarithmic amplifier and anti-logarithmic amplifier, and also its operation as a half wave and full wave rectifier. You have to know the basics of OPAMP. So and also you have to know the virtual ground concept and also the details of inverting, non-inverting amplifier, because this is the basics. So without having idea of this, it will be very problematic for you if you directly come to this class to understand the OPAMP as a logarithmic or anti-logarithmic amplifier. So in today's class, I will show you how you can use a OPAMP circuit for a logarithmic arithmetic operation or anti-logarithmic arithmetic operations. So logarithmic operation, that means your output of the OPAMP that will be equals to the log of the corresponding input. And in case of anti-logarithmic amplifier, your output will be anti-log of the given input. So hope this will be very much interesting for you. And also in my last module video lessons that I have uploaded, in that case I have shown you basics of half wave and full wave rectifier circuit using p-n junction diode. So in that case, you know that rectifier circuit basically converts the AC to a DC. Half wave, it converts only the positive half of the input AC signals, and in case of full wave rectifier, it converts the both positive and negative half of the input AC signals. So Here we will replace that p-n junction diode and we will use operational amplifier, or in short OPAMP, and we will forget the same operation. That means for half wave it will convert the or rectify the positive half of the input AC signals and give you a DC current, DC voltage. And in case of full wave rectifier, using operational amplifier or OPAMP, you will get the output as is DC. So the input, both the positive half cycle and negative half cycle, will be rectified. So I will show you one by one. So log and anti-log amplifier. The electronic circuit which perform the mathematical operation such as logarithmic, logarithm and anti-logarithm, that means exponential with an amplification, are called logarithmic amplifier and anti-logarithmic amplifier. So in this chapter I am going to discuss the logarithmic amplifier and anti-logarithmic amplifier. And you may note that these amplifiers fall under nonlinear applications. So first of all, the logarithmic amplifier. A logarithmic amplifier or a log amplifier is an electronic circuit that produces an output that is proportional to the logarithm of the applied input. This section discusses about the OPAMP based logarithmic amplifier in detail. An OPAMP based logarithmic amplifier produces a voltage at the output which is proportional to the logarithm of the voltage applied to the resistor connected to its inverting terminal. Now I will show you the circuit diagram of an OPAMP based logarithmic amplifier. So here this is the circuit of logarithmic amplifier. So what you found here, the non-inverting terminal is grounded and we have applied a voltage at the inverting terminal through a resistance R1. In feedback circuit we have used a p-n junction diode through which the diode current IF flows when the diode is forward biased. So this is the circuit of logarithmic amplifier. Now, in the above circuit, the non-inverting input terminal of an OPAMP is connected to the ground. That means 0 volt is applied at the non-inverting input terminal of the OPAMP. Now, according to virtual short concept, the voltage at the inverting input terminal of an OPAMP will be equal to the voltage at its non-inverting input terminal, so that the voltage at the inverting input terminal will be 0 volt. The nodal equation at the inverting input terminal node is 0 minus Vi by R1 plus If equals to 0. So therefore If equals to Vy by R1. So make it equation 1. The following is the equation for current flowing through a diode. When it is in forward bias, so we can write the diode current If is equals to Is e to the power Vf by n Vt. Make it equation number 2. So in equation 2, Is is the saturation current of diode, Vf is the voltage drop across diode when it is forward bias, Vt is the diode thermal equivalent voltage. The KVL equation around the feedback loop of the op-amp will be 0 minus Vf minus V0 is equals to 0. From therefore we get Vf equals to minus of V0. Now substituting a value of Vf in equation 2, we get If equals to Is e to the power minus V0 by n Vt, that is equation 3. So observe that the left hand side terms of both equation 1 and equation 3 are same. So when equating these two, we get Vi by R1 equals to Is e to the power minus V0 by n Vt, and Vi by R1 Is equals to e to the power minus V0 by n Vt. Now applying natural log on both sides, we get ln of Vi by R1 Is equals to minus V0 by n Vt. Now applying natural logarithm on both sides will give us V0 equals to minus of n into Vt ln of Vi by R1 Is. So in above equation, the parameter n, Vt and Is are constant, so the output voltage V0 will be proportional to the natural logarithm of the input voltage for a fixed value of resistance R1. So this OPAMP based logarithmic amplifier circuit discussed above will produce an output which is proportional to the natural logarithm of the input voltage. Now, anti-logarithmic amplifier. An anti-logarithmic amplifier or an anti-log amplifier is an electronic circuit that produces an output that is proportional to the anti-logarithm of the applied input. This section discusses about the OPAMP based anti-logarithmic amplifier. Now I will show you the circuit. So you can see the circuit is given here. Here the thing is that we have ground the non-inverting terminal and we have applied the voltage Vi through a diode, PN junction diode at the inverting terminal, and here it is the feedback resistance. So only we have replaced the feedback diode with a resistance, and here the resistance with a PN junction diode. So just opposite to the logarithmic amplifier. Now in the circuit shown above, the non-inverting input terminal of the op-amp is connected to ground. It means 0 volt is applied to it and its non-inverting terminal. So according to virtual ground concept, the voltage at the inverting input terminal of op-amp will be equals to the voltage present at the non-inverting input terminal. So the voltage at its inverting terminal is also 0. Now by the nodal equation at the inverting point will give us minus If plus 0 minus V0 by Rf equals to 0, for where we can get V0 equals to minus Rf If. Again same, we know the forward current of the diode, that is If equals to Is e to the power Vf minus nVt. Substituting we get V0 equals to minus of Rf within bracket Is e to the power Vf minus nVt. So V0 equals to minus RFIS e to the power Vf by n into Vt, make it equation 5. The KVL equation at the input side of the inverting terminal of the op-amp will be give, that is Vi minus Vf equals to 0. So Vf equals to Vi. So substituting this, we get V0 equals to minus Rf Is e to the power Vi by nVt. So here the output of the op-amp will be anti-natural logarithm of the input voltage Vi. Now the next part, that is rectifier circuit. As we know, we have discussed two type of rectifier, half wave rectifier and full wave rectifier using op-amp. So this one is the following circuit diagram of half wave rectifier. So here you can see the non-inverting terminal is grounded, and the inverting terminal we have applied a voltage Vi through R1 resistance, and this is the feedback connection. We have used two diodes, one is diode D1, another one is diode D2 at the output, and RF is the feedback resistance. Now the working of the half wave rectifier is that for positive half cycle of the sinusoidal input, the output of the op-amp will be negative, hence diode D1 will be forward bias. When diode D1 is the forward bias, output voltage of the op-amp will be minus 0.7 volt, so the diode D2 will be reverse bias, hence the output voltage of the above circuit is 0 volt. So therefore no zero output of the half wave rectifier for positive half cycle of the sinusoidal input. Now for negative half cycles, the sinusoidal input of the output of the op-amp will be positive, hence diode D1 and D2 will be reverse bias and forward bias respectively. So the output voltage above the circuit will be V0 equals to minus of Rf by R1 into V1. Therefore the output of a half wave rectifier will be positive half cycle for a negative half cycle of the sinusoidal input. So here this is the output of the op-amp using half wave rectifier. So here above one is the sinusoidal input and this one is the sinusoidal output. So you can see the above graph, half wave rectifier circuit diagram that we discussed produce positive half cycle for negative half cycles of the sinusoidal input and zero output for the positive half cycle of the sinusoidal input. Now I will show you the full wave rectifier. Here you can see the full wave rectifier circuit. So here the above circuit diagram consists of two op-amps and two diode D1 and D2 and 5 resistor R1 to R5. For positive half cycle sinusoidal input, the output of the first op-amp will be negative, hence diode D1 and D2 will be forward bias and reverse bias respectively. The output of the op-amp, that will be V01 equals to minus of R2 by R1 into Vy. So observe that the output of the first op-amp is connected to resistor R4, which is connected to inverting terminal of the second op-amp. The voltage present at the non-inverting terminal of the second op-amp is 0 volt. So the second op-amp is with resistor R4 and R4 acts as an inverting amplifier. So the output voltage of the second op-amp V0 equals to minus R5 by R4 V01. So substituting, we get V0 is equals to R2 R5 by R1 R4 whole into Vi. Now putting all the resistance is equals to R will give us V01 is equals to minus of R3 by R1 Vi. So the output of the first op-amp is directly connected to the non-inverting terminal of the second op-amp. Now the second op-amp with resistor R4 and R5 act as a non-inverting amplifier. So output will be V0 equals to 1 plus R5 by R4 into V01. So your V0 will be equals to minus of R3 by R1 whole into 1 plus R5 by R4 into Vi. So the input and output waveform of an op-amp are shown below. So here you can see you will get all the positive and negative half cycle of the input AC signal is rectified, and you will get a corresponding DC output. So these are considered to be the reference book that you can refer. The evaluation procedure is same. Students have to appear for 70 marks end semester exam and 30 marks internal exam, out of which 15 for exam, 10 for assignment and 5 for attendance. So all of you have understand today's video class lessons. In next class I will discuss the OPAMP based clipper and clamping circuit. Thank you.